For an internship. Yeah, nice. When is it? Cool. A week from today or tomorrow. Nice. Okay, so last time we were talking about internal loads, started internal loads. And you can think of internal loads as the loads, one part of the material that you're looking at applies to the adjacent material. The example that we kept using, and I'll just keep using this, it's sort of a nice simple example. We have a horizontal beam with an upward force in the middle of 1,000 newtons, and then two 500 Newton forces on the ends. Down. So that's an equilibrium. If you did Newton's laws on those, it would all come out in equilibrium. And the way we approached it was we first isolated, we isolate, let me give the measurements of this. So this is 0.5. Is the whole thing 1? Yeah. So this is 0.5, and this is 0.5. First, we isolated the left 0.25 meters and calculated the internal loads along that line. Along that vertical line. So we isolated the black part. That means we weren't dealing with the light blue part. That color is called cyan if you're interested. I'll try to help you be round, well-rounded people. Not round people. Oh no, I accidentally made them round people. And when we isolated this piece, this force in the middle and this force at the end weren't there. You know, they weren't on the piece that we were isolating. And then we had the internal loads, a tension, shear force, and a bending moment. And remember, those internal loads are just our new sign convention for the force vector and the couple that are applied at a fixed joint. And what we calculated was P equals 0, C equals negative 500, and M equals negative 125. The next thing we did was we noticed similarities between any amount of the beam we isolated from the left end to some point before the 1,000 Newton force. So what we saw was if you isolated just a tiny little sliver, and all this was not included in what you're isolating, the free body diagram looks like this. And if you isolate a little bit more, the free body diagram of the black part looks like this. And if you isolated almost the whole first half, you fall just short of that 1,000 Newton line. The free body diagram looks like this. And even though the amount of beam that you're isolating is very different in all these cases, the loads acting are the same. And that gives you the idea that maybe there's a way to isolate just a general piece that represents all of these and all the things in between them, where we could calculate the internal loads TV and M as functions of X, where this length is X. And so that was what we did next. So these are represented by the general free body diagram. Where you have some unknown length of beam from the left end to some right end. All of this is not included. So those forces won't show up. You have a 500 Newton force here. You have the internal loads like that. And this distance is X. And when we went through that calculation, we found that T is equal to 0, V is equal to negative 500, and the bending moment is equal to negative 500x. By the way, notice, hey, dmdx is equal to V. Is that just a coincidence? Hey, Donald! That was supposed to be like Mickey Mouse. Hey, Donald, you big goof! I don't know, like my 6-year-old son thinks that's funny. No, it appeared that you are not like 6-year-olds. So, is that just a coincidence? It is not. But that's supposed to be a cliffhanger. Okay, so now this tells us the internal loads for any X value between 0 and 0.5, non-inclusive, by the way. So it works for an x value of 0.0001, and it works for an x value of 0.4999, but not 0 or 0.5. Okay, so now let's think about what happens when x is greater than 0.5. So I'm going to do the same thing I did for the first half. I'm going to draw free body diagrams of 3 different lengths of beam, where all of them have right ends that are longer than 0.5, but not all the way to 1. And so you could have this, where we've gone just past the 1,000 Newton force. The 500 Newton force is acting here. But our isolated body, we're not going to worry about the 500 on the right end. And then the internal loads are T, V, and M. Or we could do a little bit longer piece. We still have the 500 Newton force. Still have the 1,000. And the internal loads. And then I'll do one more example where we go almost all the way to the end. You have the 500, the 1,000. We don't have this 500. Let's see. And then T, V, and M. Okay, so the key is exactly the same as the key idea when the right end hadn't made it to that 1,000, is that even though these all look different, the loads that are acting are the same. And so we're going to try to do the same thing. Just draw a general free body diagram and come up with measurements for T, V, and M as a function of x. Same thing as before. So now our general free body diagram goes from the left end to some point past the 1,000. And there's some amount of material that it doesn't consider. And we have the internal loads. And we'll say that this distance is x. So Newton's second law says 0, negative 500, plus 0, positive 1,000, plus T, negative V. I'm sort of glossing over what's going on there. Did I do that before? No. Okay, look. Don't do it like that. So we'll call this that force vector from the T is in the positive x direction. So you can think of that as the variable t times the unit vector 1, 0, and that gives you t, 0. And then that v vector has a magnitude of v times a unit vector of 0, negative 1, because it's in the negative y direction. So that's 0, negative v. And those are equal to 0. Pretty soon I'm going to start just combining these into a single vector t, negative v, because it doesn't hurt anything. So t is equal to 0, and v is equal to positive 500. And then the moment equation, just like with any statics, you can choose any about point you want, but I'm going to choose always for these general free body diagrams, I'm going to choose my about point to be all the way at the left. So what's going to produce moments? Will that 500 Newton force produce a moment? No, because the force is going right through it. What about a 1,000 Newton force? That will. Do we know what the moment arm is? How far from the about point is that 1,000 Newton force? 0.5. Yep. That, no matter what x is, that moves. If you change x, that moves where this right end is. But it doesn't change where this is. That's a force that's always 0.5 meters from the end. So the moment arm is 0.5. The force vector is 1,000. And then if you had this beam connected to this point by a hinge, and you took a hammer and tapped the force of 1,000 newtons up on this beam right here, would that beam rotate around the hinge clockwise or counterclockwise? Counterclockwise, so that's positive. And then there's the couple. We just add that on. So plus m. Does the force T produce any moment? Nope, its line of action goes right through the about point. And then what about the force V? Yeah, so it's going to have a moment arm of X, a force of V, and then if you applied, took a hammer and tapped down at that point, would the beam rotate clockwise or counterclockwise around the about point? Clockwise, so that's negative. And that's equal to 0. So now m is equal to negative 500 plus Vx. And we already calculated V. So m is equal to negative 500 plus 500x. Okay, so what we got before was we got these functions that are valid for any x values between 0 and 0.5. And then with that second general free body diagram, we got these expressions that are valid for any x's between 0.5 and 1. So what we have is a pointwise function for each of these. So t is equal to 0 the whole way, just, there wasn't anything going on horizontally. The shear force is equal to negative 500 for any x values between 0 and 0.5, not including the endpoints. And positive 500 for x values between 0.5 and 1. And these are all functions of x. I suppose I'll write it like this, even though these are both piecewise constant. M, you see the dependence on x. So on the first half, m is negative 500x. That's for x's between 0 and 0.5. And on the second half, m is equal to negative 500 plus 500x. And we can plot these. So if you plot the tension, as a function of x, you just get 0 the whole way. The shear force as a function of x, we got negative 500 for the first half, positive 500 for the second half. And then for some reason, people connect them like this. Really, we don't know what the value is right at that point. So this is positive 500, this is negative 500. And then the last one, the bending moment is a function of x. Is piecewise linear, like that. So internal loads are always going to be given as piecewise functions like this. And that means that we have to know where the boundaries are between the different subfunctions. In other words, where do you have to switch from one general free body diagram to a new general free body diagram? I like the name general free body diagram. It's like a all-star wrestler name, possibly, if anyone's looking for like an identity for like a physics, you know. Yeah, exactly. And also sort of military theme, you know what I mean? It sort of mixes them up. So where are the boundaries between the subfunctions? And so here's where those boundaries occur. The boundary points are the endpoints of the beam. And then the location of any point load and then third, any location where a distributed load function changes. We haven't done internal loads with distributed loads yet, but we'll get to that. So any location where the distributed load function Q of X changes. Okay, so let's do another example. Well, first let's look back at the example we just did and see how that worked out. So here was the body. We didn't have any distributed loads in this. So if we're looking for the places where the subfunctions change, there's the two endpoints, so that's two places. And then there's only one other point where there's a point load, so that's the third one. And so if you have, if this gives n boundary points, you're going to have to draw n minus 1 general free body diagrams. And I'm going to call that cuts, because these general free body diagrams are pieces that you have an imaginary cut between what you're isolating and the rest of the beam. So n minus 1 cuts. Okay, so let me do another example. So we have a beam with a pin joint at the left, a roller in the middle, and a 1,000 Newton force that makes an angle of 45 degrees with the horizontal like that. And let's say this is 0.1 meter, and this is 0.1 meter. And we want to calculate all the internal loads. Let's go back for a second, just look back at this example. So we have these piecewise functions that represent those internal loads. And in this simple example, what we have shows us exactly where on this beam we're most concerned about this thing breaking. Like where we would want to have more material, or if it's a hollow tube, maybe we want the walls to be thicker, or maybe we want a different kind of material there. If you look at this example, you might be able to tell, this is a simple case, so you might be able to just tell by eyeballing this that you'd expect it to break right in the middle. But that's what this tells us when we look at these internal loads. Let's look at those graphs. The tension never changes, so that doesn't prefer one spot over another. The magnitude of the shear force never really changes, except we don't know what it is right at that midpoint. But anywhere that's not exactly at the midpoint, the magnitude's the same, so that doesn't really tell us anything. But the bending moment tells us that we expect this thing to break, if it breaks, somewhere close to the middle. And, that's exactly what would happen if you took a pencil and applied forces like that. Okay. So now this example. Well, the first example I gave with all the external loads applied. This one I didn't, so we have to take the extra step of calculating the external loads before we go to the internal loads. So first I'll do a free body diagram of the whole thing. And we're ignoring the weight on this. So at the pin joint, we have an unknown force vector. I'll call that RA. In the middle, we have a normal force from that roller. Call that N. And then at the right endpoint, we have that's force vector at a 45-degree angle and 1,000 newtons magnitude. So if I write that as a vector, that's positive 707.1, negative 707.1. So Newton's second law says RAX, RAY plus 0N plus 707.1, negative 707.1 is equal to zeros. And the moment equation, I'll put the about point here again, says what's the moment arm, this about point for this force N. Yep, 0.1. N, and then would that make it rotate clockwise or counterclockwise around that red dot? Counter, so that's positive. And then the horizontal component of this force at the right end wouldn't produce a moment. Right, that's just pulling on it. The line of action goes right through the about point. That downward force of 707.1 would produce a moment. What's its moment arm? Yep. Yep, so 0.2, the force magnitude is 707.1. And then that force is down. Would that make it rotate clockwise or counterclockwise? No, negative. And that's equal to 0. So we have 0.1 n is equal to 141.4, I think. And then, so n is equal to 1414. And then RA is equal to negative 707.1, negative 707.1. And if you don't like calculating the moments this way, you could write out the row vector and the force vector and the moment and do the cross product. But this is just a little quicker way to do it for horizontal members. Okay, so now we're going to do the cuts. So now we have to think about where are the places where the subfunctions can change for those piecewise functions. Well, the rules are at the endpoints and anywhere there's point forces, and then some stuff about distributed loads that we don't care about. So the endpoints, that's 2 spots. And then just like the last problem, the only other spot besides the endpoints is the middle. So the subfunctions can change here, here, and here. That means n is equal to 3. And that means we're going to do 2 cuts. One that represents a piece before the right end point of our cut gets to the middle, and 1 represents when the right end of our cut is between the middle and the end. Any questions yet? Okay, so cut 1. So cut 1 is valid for all x's between 0 and 0.5. Point 1, yes, sorry. So we're looking at, this is our general free body diagram. There's all this part of the beam that we're not including. So there's this upward force from the roller that isn't part of what we're including. There's this force vector over here that we're not including. All that is happening is a force vector at this end of negative 707.1, negative 707.1. And then the internal loads, T, B, M. So Newton's second law says negative 707.1, negative 707.1 plus T0 plus 0 negative V equal to zeros. P is equal to positive 707.1. V is equal to negative 707.1. And then the moment equation. And remember that this distance in our general free body diagram is x. So that's going to come up in the moment calculation. So Rn2L. The about point is here. And in these cuts, you always want to choose the left end point to be the about point. So what's the moment produced by the force at the left? 0, yep. And then what's the moment produced by T? 0. The bending moment, you just add in a couple. And then that V appears the same way it always does. You have a moment of X, force of V, and if you apply the downward force V at that location, and that was the hinge, it would radiate clockwise. So that always appears as negative Vx. So M is equal to Vx. And so M, since we already calculated V, M is equal to negative 707.1x. Hey, look. EM dx is equal to V. Dot, dot, dot. You don't have to say the dot, dot, dot. That's just punctuation. Okay. I was sort of thinking maybe if I did it again, it would get funnier, but. Yeah, that's true. So now the second cut. Anybody have any questions about the first cut? So now we're going on to the second general free body diagram. And this This one brings up a point that is really easy to get confused about. So I'll bring it up when we get there. Cut 2 is valid for all x's between what and what? 0.1, 0.2. Not including 0.1 or 0.2. Now look at what I draw for, like, what's the part that I isolate? The part I isolate goes all the way from the left endpoint to x. So it's not including the force at the end. It is including the roller force. What was that? 14. And then we have the forces over here. Was that negative 707, negative 707? And then the internal loads. And this length here is x. Okay, so, I mean, I go so far as to say every single one of you will get confused about this. Actually, this will be even more discouraging. This is going to make sense to every single one of you, and then at a later time, it's going to stop making sense again. You're going to go back and forth for a while. So it's sort of a weird thing, but it's tricky. You need to pay attention to this. So this is valid for x's between 0.1 and 0.2. Well, then this is 0.1 where this force is. Why am I isolating? Why am I including all this stuff over here? Yeah, that is where we choose the about point. I mean, really, I'd say that the easiest, the best explanation is the only thing we want is we want to be able to calculate these values on the right end at some value x that's between those. So all we need is for the right end to be between these values. You know, as far as where the left end is, we're just choosing that to make this problem as simple as we can. All we want is a way to calculate those. If we chose the left end to be in here somewhere, that would give us another set of internal loads to calculate, and that would be unnecessarily difficult. So we're always going to start all the way at the left end and go to x. And the range of x values only talks about the right end. Okay, so that might already be confusing, or it'll be confusing at 12:35 at night some night. You know, sorry, that's just how it is.
That makes sense for the left or the cut 1 too, because you're going inclusive of, or like up to the x. Technically, it's still right for the cut 1 because for the first one, it's 0. It's inclusive of 0.
Right.
There's just nothing there.
That's right. Yeah. That's right. So Newton's second law says negative 707.1, negative 707.1 plus 0, 1414 plus T0 plus 0 negative V. I'm going to just start lumping these, save electronic ink. T is equal to positive 707.1. V is equal to positive 707.1. And then the moment equation, if this is the about point, the force at the left doesn't produce any moment. What's the moment arm of the 1414? Yep, 0.1. So moment arm of 0.1 times the magnitude of the force, 1414. And then would that upward force make it rotate clockwise or counterclockwise? Counter, so positive. And then plus m minus Vx is equal to 0. So m is equal to negative 141.4 plus Vx. So m is equal to negative 141.4 plus 707.1x. What? Yeah, weird. That's so weird. What's happening? Yeah. I'm not doing that anymore.
Come on.
No.
One more.
You had your chance to pretend like you liked it. Okay, so now these functions, the tension is positive 707.1 everywhere. The shear force, negative 707.1, positive 707.1. So it's negative 707.1 for x's between 0 and 0.1, and positive 707.1 for x's between 0.1 and 0.2. And then the bending moment is negative 707.1x for x's between 0 and 0.1, and negative 141.4 plus 707.1x for x's between 0.1 and 2. And so if we plot this, the tension is positive 707.1 the whole way. The shear force is negative 707 and then positive. And the bending moment is a piecewise linear function. It goes down to negative 70.71 and then comes back. You can see it's a linear function, and so you could just punch in x's at the endpoints of those intervals, and you can see what it does. Negative 70. Okay, so where are we concerned about this breaking? Yeah, it's the same as the last one. You know, basically, this time the tension, there is a tension, but it's the same everywhere. Shear force magnitude is the same everywhere. And then the bending moment gets bigger the closer you get to the middle. Anybody have any questions about this one? Okay, there are five things that you can check in these problems that can help you find mistakes, and it's easy to make mistakes because there's a lot of just little calculations in this. So 5 checks for internal loads. Who wants to guess what the first one is? Yeah. dmdx is equal to v. yeah, I made you want it. Classic professor trick. And this has to be true at every point. The second one, we haven't talked about distributed loads yet. We'll get to that next. But dv dx is equal to the negative of this function q, where q of x is a downward distributed load. And again, this has to hold at every point. And now we have 3 things that have to hold at the endpoints. Number 3, the tension, no, don't write that. At each endpoint, the tension is equal to 0 if and only if there is no horizontal point force at endpoint. Yes, that's right. Yeah, so these are all external. And 4 and 5 look pretty similar to 3. It just has to do with shear force and bending moment. So number 4, at each endpoint, v is equal to 0 if and only if. What do you think this is going to be? It makes sense if you think about what the shear force is. What? Yeah, right. So v is equal to 0 at the endpoint if and only if there's no external vertical force at that endpoint. And then the last one has to do with the bending moment. So at each endpoint, m is equal to 0 if and only if. What do you think this one's going to say? Yeah, couple. So if and only if there's no external couple, there's no distributed couples. So I'm talking about a point couple here. No external couple at that end point. Okay, so we can check these. We already, as we were going through with each cut, we noticed that dm dx is equal to v. So that one holds. The second one, we don't have any distributed loads. So that function describing the distributed loads is 0. So what we need for number 2 is at every point, dv dx has to be equal to 0. And that holds in these cases because v is a constant for both cuts. So derivative of negative 707.1 is 0. Derivative of positive 707.1 is 0. And, well, any questions about the first two of those? Here's something that you might think about. Since we know these derivative relationships, couldn't we just integrate the distributed load function to get the shear force, and then integrate the shear force to get the bending moment, and not go through all the Newton's laws stuff? And there is something to that. The problem is, as you saw, when you, so what we would have is v is equal to the integral of negative q, But when you take that integral, you get a constant of integration. And we'd have to figure out a way to calculate that constant of integration, which really isn't any easier than the way we're doing it. So, and the same thing with this step. Those constants of integration just cause problems. And otherwise, we would just integrate and not even worry about Newton's laws. All right, so now the endpoints. At the left endpoint, is there a horizontal point force? Yes. At the right endpoint, is there? So it should be the case that we have non-zero tension at both endpoints. And we have that. So that check holds. And then are there vertical point forces at the endpoints? There's one at each. So we should get non-zero shear forces at both endpoints. And we do, so that one holds. And then the last one, are there point couples? Are there couples at either of those two endpoints? Nope, not at a pin joint, and that one just has a point force. So the bending moment should be 0 at the two endpoints, and they are. Yep. Mm-hmm. Nope. So just if there's a point couple at the endpoint, it's going to be a non-zero bending moment at the endpoint. Yeah, still. So the way that works, so if there's one at each end, and they cancel each other out, that's actually a case where you'd have a constant bending moment through the whole thing. That's what you call pure bending. There's no forces. You're just taking this thing and trying to flex it up. And so, yeah, that's the one case where you would see a constant bending moment. Any other questions? Okay, let's do one with distributed loads. So when we're trying to calculate, do any calculations with distributed loads, the first step we take is to represent the distributed load as a point force, right? Like the weight, for example. Weight is a distributed load, but we represent it as a point force acting at the center of mass of the body. Now you have to be, with internal loads, you have to be careful about when you take that step of representing a distributed load as a point force. You can only represent a distributed load as a point force after you choose the body to isolate. So here's what I mean. So if you have something like this, so let's say this has a length of 1 meter, and this distributed load is 800 newtons per meter. And then each one of these two forces would be 400 newtons. And we're used to just taking that and representing it as a point force of 800 and 2 point forces of 400, right? What you can't do now is do a cut like this, where you assume that the 400 is here and that you haven't gotten to the weight force yet, and you haven't gotten to this other 400. This is illegal. Okay, and it makes sense. I mean, weight acts on every bit of material, so it wouldn't make any sense that weight is not affecting anything at all until your cut passes the center of the beam, like that just doesn't seem right, So what you have to do is you have to choose your body to isolate. Still representing this as a distributed load. And now once you've chosen the body to isolate, you've actually committed to a free body diagram. Now you can represent this as a point force. You get this here. You're skipping all this stuff. So if this was 800, now the weight acts at the center of the piece that you've isolated, not at the center of the whole body. It has a magnitude equal to the area of that shape, which in this case is 800x because this is x. And you have the 400. Do you understand the distinction I'm trying to make there? Okay. Should we go around the room? Pete understands it. If Pete understands it, anyone does.
I remember that.
Well, I mean that in a nice way. So you can't just treat the distributed load like a point force and then keep it there for every time. When you make the cut, it's a distributed load, and then you make the switch. So let's do a problem where, well, yeah, let's do a problem just like this. Let's say we have a beam it makes a fixed joint with the wall on the right end. And let's say there's a tension over here of 1,000 newtons. The length is 2 meters. And let's say that the mass of the beam is 100 kilograms. What are the internal loads? One thing to notice here, if you ever get a problem like this, that's a cantilever beam connected on the right end, it can save you some time to notice that you can skip calculating the external loads, because when we make the cuts, we never get all the way to the right end. So we can do this without calculating the external loads at the wall. So notice for cantilevers, connected at the right, you can skip the step of calculating the external loads. Okay, so let's think about how many places there are where the subfunctions can change for these pointwise functions. The endpoints, so there's 2, and then are there any places besides the 2 endpoints where there are point forces or where the distributed load changes? Nope, there's no point forces, and the distributed load is a uniform distributed load representing weight, and that's all we have. So n is equal to 2, and that means we just have to do 1 cut. So our cut represents all the x values between 0 and 2. And it looks like this. We're just taking some arbitrary amount of this beam and skipping some other amount. The stuff happening over here at the wall, we don't care about that. Some of that weight we don't care about, but some we do. And then we have the internal loads. And we have to figure out what that distributed load is. Well, if the mass is 100, what's the total weight? Yeah, so the weight is 981. And since the length is 2 meters of the whole thing, so that function Q, representing the downward distributed load, is equal to 981 over 2 equals 490.5 newtons per meter. So this distributed load has the magnitude of 490.5 newtons per meter. And the length is x. So now we have to think about how to represent this distributed load as a point force. And the idea of how you do it is exactly the same as it is if this isn't a variable, if that's a number. You can imagine drawing out the shape. The height is 490.5. This time, instead of being a number, the width is just x. The centroid of this shape is in the middle. And the magnitude of the point force is the area. And what's the area of this rectangle? Yeah, 490.5x. So now I'll redraw the free body diagram. Right in the middle, we have this force of 490.5x. That's the weight. And then we have the internal loads, T, V, and M. And then Newton's second law says 0, negative 490.5x plus T, negative V is equal to 0. Oh, shoot, there was a force there, wasn't there? Should we get rid of the force or add it to the things lower? Okay. It's never there. You can't do that on tests, though.
Well, we
Yeah, that's true. Yeah, it's a free country. So T is equal to 0. V is equal to negative 490.5x. And now, for the moment, we need to know these distances. The whole thing is x. To the centroid of the rectangle is x over 2, and then this is x over 2. So the moment equation, we have a moment arm of x over 2 times a force of 490.5x, and the about point is here. So would that make it rotate clockwise or counterclockwise? Clockwise, so this is negative. And then plus m minus vx is equal to 0. So m is equal to positive 245.25x plus vx. Yes, thank you. 245.25x squared times v times x plus v times x. V is this thing. So we get m is equal to 245.25 x squared minus 490.5 x squared. And so your final function m is negative 245.25 x squared. And let's do those two derivative checks. dm dx is negative 490.5 x, and that's equal to v, so that one works. And negative dv dx, dv dx is negative 490.5. Negative of that is positive 490.5. That's equal to our downward distributed load function, q of x. So those two both work. Oh, one more thing about the checks at the endpoints. This can be a little confusing with distributed loads. Is there a point force acting at the left end of this beam? No, there's a distributed load, but that's not the same as a point force. And so that means that the shear force at this end has to be equal to 0. If we had gone ahead and calculated the external loads at the wall, we would see point forces there, and so the shear force is going to be non-zero at the right end. Okay, any questions? All right, have a good weekend. What did we talk about the next test? When is it? We haven't talked about it. Let's look. Oh, we did, okay. Is that on Tuesday? Okay. And we're doing, it's everything up through structures, right? Okay, good.